Okay, so in your note packet, we're looking at the Doppler effect. So this is our last major topic for this chapter, and so we're looking at testing on this stuff sometime next week. So Doppler shift, we're going to finish this up today, tomorrow kind of time frame, and then what we have is we have a presentation on Friday. Probably do a little bit of review. I'm expecting that we should be able to test on chapter 12 midweek next week. Okay, so not Mondays. I don't like Mondays that much. But probably Tuesday would be appropriate. Okay, so we're nearing the end of this. Doppler effect occurs whenever there is a relative motion. So whenever there's motion between a source of a wave and a receiver of a wave, we get something called the Doppler effect. Now, for sound, it's probably the easiest one for us to associate is with sound, but anything that travels as a wave experiences Doppler effect. So Doppler effect for sound, you observe change in frequency or pitch when there's relative motion between the source of sound and an observer. So it occurs with water waves, it occurs with light waves, it occurs with sound waves. Anything that propagates as a wave will experience a Doppler shift. Does this occur with particles? No. Particles would not be related to have any Doppler shift. What happens, or why do we have it? It's because of the constancy of the speed. The reason that we have Doppler shift is because the speed of the wave does not depend on the source speed. If the source is stationary, like the fire engine on the very top picture, the speed at which the sound wave travels is the same in both directions, but it also would be exactly the same as if the fire truck is moving. If the fire truck is moving, the speed of the sound wave is exactly the same as it was before. Now that doesn't work with particles. As an example, if I were on this stationary fire truck and I threw a baseball at 50 miles per hour, are you ready, Julian? I threw a baseball at 50 miles per hour towards Julian. That ball is going to be traveling at 50 miles per hour relative to the ground. However, if I were, I had the same trouble. If I were riding on that fire truck, as a matter of fact, I was a pitcher in high school. I could throw the ball maybe about 70 miles per hour. That's about the best I could do. I could have made it to the major leagues if I could have made it 90 miles per hour. But I couldn't get it to above 70. So if I could ride on, and I told them, I said, hey, if you could just allow me to ride on, let me get into the back of a pickup truck and have that pickup truck drive in from center field at 20 miles per hour, right? So I drive in from center field at 20 miles per hour. I'll make sure I pitch it when I get to the pitcher's mound. But if I could throw the ball at 70 miles per hour and the truck was traveling at 20 miles per hour, how fast would that ball be traveling relative to the ground? 90 miles per hour. They wouldn't allow me to do it. I don't know why. They would not allow me to ride in from center field on a truck 20 miles per hour. What would they add? Would the velocity add? Yeah, but that doesn't happen with sound. If that fire truck is moving at 20 miles per hour, the speed of sound does not travel at the speed of sound plus 20. So what that means is that those waves can be compressed in front and sort of spread out in back. Now there is a visualization of that, so you can sort of see it. This is going to that same site that always takes a couple odd seconds for it to load. But this is showing you what would happen if you're having a source of sound moving. There it is. Okay. Now, there's an equation that we're going to look at. But here is a stationary source. You notice that the sound waves appear to, if it's sound, they appear to be propagating in all directions equally. I look at the wavelength. That doesn't matter where I look, but the wavelength would be the same no matter if I'm looking towards the right, towards the top, towards the left, or towards the bottom. Wavelength would be the same. However, if the source is moving now, and so this gives you a sense of what's happening, you notice the speed at which those waves are propagating are exactly the same as they were before. But now it's moving in the direction towards the right, which means the wavelength, would you guys agree the wavelength appears to be shorter towards the right than towards the left? If the speed is the same and the wavelength becomes smaller, what does that mean about the frequency? Yeah, if the speed is the same, because remember, velocity is equal to frequency times wavelength. If I make the wavelength shorter and the speed is the same, what should happen to the frequency? Should increase. So what that's showing is if the wavelength becomes smaller, which it does, that would mean the frequency at which you're hearing that wave is going to decrease. And so even though the source is emitting maybe the same frequency of sound, if you're in front of that, you're going to hear a higher frequency than if you're behind it. And so that's what we call Doppler shift. And so if there's relative motion between the source and the receiver, you're going to hear a different frequency than what's being emitted. Now this is this is at the sound barrier. And so one of the applications of Doppler shift is in order for you to break through the sound barrier, and by the way, why do they call it a sound barrier, do you think? Say it again.
That's the speed of sound. So if it went faster than that, the sound would travel behind.
The breaking the sound barrier, and it truly is a sound barrier, is that it was difficult to do because as they get closer and closer to the speed of sound, remember sound or pressure waves can build on each other, right? They can add superimpose. And so what's happening here is all of those pressure variations created from that jet, in this case, can build on top of each other, and it's like literally creating a wall of pressure. And so they're like, oh, you got to punch through that sound barrier. And so if you look at that, you can see the really dark, bold lines where all of those pressure waves, those pressure fronts, if you will, are building on top of each other. Well, it took a while for them to figure out how to punch through that. And honestly, what's happening is as that aircraft is going faster and faster and faster, it's like there's a wall that's trying to penetrate to be able to get through, and that has to do with the pressure building up. And then finally, they have to like punch through that wall. And so they're traveling at the speed of sound. Now, if you travel faster than the speed of sound, then what you're going to be doing is you're going to get out in front of that pressure wave. And so the shape of that cone, the faster you're going in relation to the speed of sound, the more narrow that cone is. And so there are trig relationships you can go through to be able to determine just how the speed at which you're traveling is related to the shape of that cone. I don't think we're going to have time for us to be able to go through and do that analysis, just because we have other things we got to look at. But that's yeah. Go ahead.
Where's the sonic boom on the
okay.
wave? Where would that?
Good. Let's take this for a moment. Let's say that I'm standing right here. I'm standing right at that particular spot. I'm gonna change this over so I can actually draw on this for a second. So let's say that I'm standing right here on the ground. The aircraft is going over. I'm not going to hear anything until the sound from that aircraft gets to me. Now you notice that, I'm going to try to go back to the other one for a second. Well, actually, let me try it. If I'm just right here, you notice. Actually, let me go to this one. I'm not moving. That thing. I hear it takes maybe a moment for that sound to reach me, right? But I'm not going to notice anything. I can see it. I can hear it. All that kind of stuff. That's fine. However, if that source is moving relative to me, you notice here I'm in front of that thing, so I'm going to hear a higher frequency than if I were behind it. If I were to switch that, and I don't know if I can move that, I can't really get myself to the other side there. But if I were on the other side of that, I'd hear a lower frequency if it's moving away from me. But look at this one here. You notice if I'm standing right here, I'm not going to hear anything. That aircraft could be coming in from the left. I don't hear anything until right now. And what I hear right when that pressure front hits me is not a single pressure wave. What I hear is a combination of pressure waves that are built up top of each other. That's why they call it a sonic boom, right? Is that I'm hearing all of that pressure at once, and it would be right there. I hear that sound, and it's all of it. Now, if I'm going supersonic, that thing's already going to have passed me. Do you notice that it's already gone past me by the time that sound cone gets to me? Okay, you've been to an air show before and heard like a sonic boom from something. Have you seen? Okay. it's not very pleasing, right? If they run those in residential areas, I mean, those booms can cause some problems with with the community and stuff like that. Supersonic flight, they don't really like to even have those, even though they have piloted that for commercial purposes to say, hey, let's fly supersonic over to England. Great, it only takes 2 hours to get there instead of whatever. The problem is that it creates a lot of havoc with communities because of the sonic booms. Okay, we're not going to study that in detail. What we're interested in more is the equation that describes the Doppler shift. And I want you to take a moment and see, look at the equation that describes it. And I want you to point out or pick out one thing that seems odd to you, because you should see something that looks odd. It's the thing that causes people most of the concern. F prime represents the shifted frequency, so it's the frequency you would hear. F represents the actual frequency. VW, speed of the wave. If it's sound, we could use 331 plus 0.6 T. If it's light, we'd have to use a slightly different equation for Doppler shift for light, but regardless, it's the speed at which the wave moves. VD represents the detector. If I'm the one listening, I would be the detector. If I'm the one producing the sound, I'd be the source. What do you notice that looks confusing on that equation? Looks like a derivative?
No, I meant F prime, the notation.
Yeah, that's just notation stuff.
Minus or plus.
Okay, that's an important thing. You notice that in the numerator, really guys, this is 4 equations in one. I can have either the detector moving toward or away, I can have the source moving toward or away. This equation can handle 4 different kinds of things. So the sign that you choose depends on which way the object is moving relative to, like, from the source or towards the source or away from the source. So the plus or minus on the top, and you notice on the bottom it says minus or plus. The reason for that is that you choose the appropriate sign based on which way the object is moving. So it's not a typo. It's plus or minus and minus plus for a reason. You'd use the top sign, always the top sign. Use the top if the motion is toward. If the motion of the detector is toward the source, you'd use the top sign. If the motion of the source is towards the detector, you would use the top sign. So you got to look at whether or not the object is moving toward or away. You would use the bottom sign then if it's away. So whether or not you use the top or bottom sign depends on which way that object is moving relative to the other. So you have to make a choice as to which way that thing's going. Probably the easiest way to do this is through numerous examples. Okay. So ice cream truck, I don't know if you guys know this or not, but 2,500 hertz from an ice cream truck is specially designed to sort of get you excited to eat ice cream. I don't know if you guys know that. It makes you sort of resonate with that ice cream truck. Did you guys know that? That when you hear 2,500 hertz, it gives you a sense of you want ice cream. That's why the ice cream trucks all play that sound monotone. I'm just messing with you. It's not true. Apparently people, they're not buying it. Anyway, an ice cream truck is sounding its horns monotone 2,500 hertz, a little bit higher frequency than that other one. At what frequency does Billy hear the horn if Billy is stationary and the truck is moving toward him at 15 meters per second? So Billy's at rest, the truck is coming towards him. What we want to do is determine the frequency that Billy hears. So for these first couple, I'm going to draw a picture. So that's the ice cream truck. Here's Billy. And the ice cream truck is moving toward him at 15 meters per second. Billy is the detector. The ice cream truck is the source. Okay, so you have to know who's who. We have the source moving towards the detector, and we want to hear the frequency that the detector hears. Now, this is emitting a frequency of 2,500 hertz. But what Billy hears is not the derivative of that. Thank you. It's not the derivative of that frequency. It's the frequency that he hears. Now, first, would you guys agree he's going to hear a higher frequency than 2,500? How much it's shifted depends on how fast that truck is moving and how fast the sound wave moves. So when we go to do this, we would say that the frequency that he hears is equal to F, which would be 2,500 hertz, multiplied by. And this thing here that we write is going to be a pure number. It's going to be a factor. It's either going to be above 1 or less than 1. So I'm either going to shift the frequency up or shift it down. The speed. Now, you notice I didn't give any temperature here. What should we assume to be the speed of sound through that air? 343, right? So if we don't give a temperature value, then it's going to be 343, which is the velocity of the wave, speed of sound through air. Now, plus or minus the detector. The detector is at rest, so I don't need to use any term for that. So plus or minus would be 0, doesn't matter. So in the denominator, I look at using the appropriate sign based on the source moving. Now the source is moving, would you guys agree the source is moving towards the detector? Toward means top. So I'm going to use the top sign. For the denominator, the top sign is a negative. So I subtract from that the speed at which the source is moving. Now, I didn't write my units there because it gets hard for me to write on that board, but you notice every one of those is meters per second. The denominator becomes smaller than the numerator. This factor becomes bigger than 1, and then I just multiply that by that frequency to get that new shifted frequency. If you have a calculator, just shout that out for me once you get it. Were you able to get a frequency? I'm getting, with my fancy dancy calculator here, 2614. Is that what you get?
Yep.
So Billy hears a different frequency than what's being emitted. It just has to do with the fact that the source is moving toward him. Okay. Now, the next one. At what frequency does Billy hear the horn if the truck is stationary and he's an Olympian able to run at it at 8 meters per second? So he really wants that ice cream. He's going to hear a shifted frequency, but now what we have is the detector moving, not the source. Okay. Now I know the sound waves look like they're symmetric through space, but Billy is the one that's now running toward it. And so even though it looks like those sound waves are equally spaced in each direction, there's relative motion between the source and the detector. He's still the detector, so he's moving this way now. Velocity of the detector is 8 meters per second, and he's going toward that stationary source. So we go through it. I want to determine what that frequency is. It's still emitting 2,500 hertz. 343 is still the speed of sound. We're going to divide that by 343. I notice the source is now stationary, so it's minus plus the source. I don't care what that number is because it's 0. But we use the top sign for the detector. Is that top sign for the numerator, is that positive? So we would add to that 8 for that. That's going to make the numerator bigger than the denominator. Again, we get a Doppler shift that's higher frequency than what we emitted. 343 plus 8. Is it over? Okay. What time is it?
12:53.
Have a great day. So folks, tomorrow we'll finish up Doppler shift stuff, and then we will go from there. Thank you guys for bringing in the instruments. I hope that wasn't too much of a hassle for you.